Hey guys, today I want to present a solution to the International Math Olympiad 29 problem 5. At first, let's have a look on the problem statement. We are asked to find all functions from the positive integers to the positive integers such that a, f of b and f of b plus f of a minus 1 are the sides of a non-degenerate triangle for all ab from the positive integers. These three sides form a triangle if and only if the triangle inequality holds. This means that the sum of two of these three lengths must be greater than the third one. So these three inequalities are equivalent to the problem statement. Here we remember that we work in the positive integers. This means that the left-hand side in these three inequalities is always at least one greater than the right-hand side. Therefore, we can say that these three inequalities are equivalent to the following three. Namely, we can write a greater than or equal sign and add a plus 1 to the right hand side. Since we only have two function terms in our inequalities and see that they are swapped in inequality 1 and 2, namely in the first inequality they are that way around and in the second inequality they are swapped, we are motivated to plug in a small values for a. So let's try a equals to 1 and let's plug this into equation 1 and into equation 2. So if we have a look on these inequalities, we see that in inequality 1 the a equals 1 cancels out with the 1 on the right hand side, and same happens for inequality 2. Therefore we get that f of b is greater than or equal to f of b plus f of 1 minus 1, but this is from inequality 2 also greater than or equal to f of b. Therefore, we must have equality. In this equation here, we see that if f of 1 is equal to 1, then everything is fine and the equation is obviously true. But in the case that f of 1 is not equal to 1, we see that the function is periodic, and therefore, let's have a closer look on this case. We assume that f of 1 minus 1 is equal to k, which is greater than 0. And from this, we get that f of b is equal to f of b plus k. Now we see that from this equation and the fact that we work in the positive integers, the function only can take the values from f of 1 up to f of k. Therefore, we know that the function is bounded, and we can write that f of x is less than or equal to the maximum of f of 1 up to f of k. Let's call this n. If we have a look back to our three inequalities here, we see that in our third inequality we only have function terms on the left hand side. But the left hand side is greater than or equal to the right hand side, and on the right hand side we have a, which can be arbitrarily large. We can get a contradiction out of this, namely taking a equals to 2m into our equation 3 gives that f of b plus f of b plus f of 2m minus 1 is greater than or equal to 2m plus 1. And now we can use this inequality here, and this tells us that the left hand side is less than or equal to 2m, so we have 2m is greater than or equal to this term here, but this is greater than or equal to 2m plus 1, and this is clearly a contradiction. This tells us now that our assumption f of 1 minus 1 greater than 0 was false. Therefore, f of 1 is less than or equal to 1, and since we work in the positive integers, f of 1 must be equal to 1. Now we can do the same thing as in our first step, because we can now plug in b equals 1, and then we also have that f of b must be equal to 1. But this time we use equation 1 and 3, and here we also see again that f of 1, which is equal to 1, cancels out with the 1 on the right hand side, and same happens in inequality 3. And then we have that a is greater than or equal to f of 1 plus f of a minus 1, and this is again greater than or equal to a. Therefore, we must have equality. So we get that b equals 1 into the inequalities 1 and 3 yields that a is equal to f of 1 plus f of a minus 1, and this is equal to f of a. Equations like this, where you have an f of a term on one side and a single a term on the other side, are really good in functional equations, and you should keep them in mind, because from such equations we can directly follow bijectivity. In this problem we only need injectivity, and therefore I will only prove this. So let's assume that f of a is equal to f of b. Then we can say that f of a is also equal to f of b, and now we can use this equation here to directly get that a equals b, and therefore the function is injective. Now let's go on plugging in small values for a into inequality 1 and 2. So our next try is a equals 2. Similarly as before, we can now use inequality 1 and 2 to conclude that f of b plus 1 is greater than or equal to f of b plus f of 2 minus 1, and this is greater than or equal to f of b minus 1. Now we remember that f is injective, and therefore f of 2 can't be equal to 1, since f of 1 is equal to 1. Therefore, this term here in the middle is not equal to f of b, and now again, since f is injective, we know that this term here in the middle must be equal to f of b plus 1 or to f of b minus 1. So let's write down that f of b plus l is equal to f of b plus minus 1, and here we want l to be equal to f of 2 minus 1, and we know that this is greater than 0. This equation can be now used repeatedly, and we can say that f of b plus 2l is equal to f of b plus l plus minus 1, and this is now equal to f of b plus minus 1 plus minus 1. Since l is greater than 0, we know that b plus 2l is not equal to b. And now, since f is injective, we know that the plus minus 1s on the right hand side can't cancel out. Therefore, we must have in both times the plus, or we must have in both cases the minus. If we repeat this argument, and starting with some b and then adding always a plus l into the argument, we must always have the same sign in front of the 1. Therefore, we can conclude that f of b plus n times l must be equal to f of b plus minus n. But here we see that if we choose n large enough, such that n is greater than f of b, minus is not possible because we only work in a positive integer, and therefore f of b plus nl must be positive, and so only the plus sign is possible. Now b equals 1 and n equals 2l gives that f of 1 plus l squared is equal to f of 1 plus l, but now l is defined as f of 2 minus 1, and f of 1 is equal to 1, so this is equal to f of 2. F injective now gives us that these two arguments here must be the same, so we get that 1 plus l squared is equal to 2, and since we have that l is greater than 0, this directly implies that l is equal to 1. Taking this equation again and plugging in b equals 1, we get that f of 1 plus n times l, which is nothing but n, is equal to f of 1 plus n, and this is equal to n plus 1. Since f of 1 is 1, we conclude that f of n is equal to n for all n from the positive integers is the only possible solution. F of n equals n indeed satisfies these three inequalities here, and these three inequalities are equivalent to the problem statement, we know that this is indeed a solution, and therefore we are done.